Okay, so the first step in creating the pipe work is to create a drawing with some sort of design intent. That way we can use it more than once. So we're going to need two things. First of all, we're going to need a profile of what the pipe looks like. What we're going to say is a 6-inch pipe. Pipe often comes in imperial. So we could convert, but the way Onshape works, we can type directly in. We can just type 6. Even if your settings are set up for metric, if you type in 6 inches, it automatically knows that's 152.4mm diameter, which is really good. Now we could add, this is going to be a 3mm wall thickness. We could add 3mm on to each side, but that doesn't do anything for our design intent, because if we scale this up, we'd like to keep it with 3mm wall thickness. So if I just calculated the diameter of this, then when if I wanted a different pipe thickness, a different pipe diameter, I'd not only have to change the inside, I'd have to change the outside as well. So for my design intent, I'm going to measure the gap between the two, because that's what I'm bothered about, that it's, as we said, a 3mm pipe wall section, so 3mm. That way, if I do change the internal diameter, the external diameter will keep 3mm away from it all the time. So that's the design intent. It means it can be modified a lot more easily down the line, cleaner model. So that's the profile of a pipe. I've drawn it on the top plane because when we do the simulation, we're going to want the air going up to start with. It'll help in the Z plus axis. So draw it on the top plane. So now we've drawn the profile. We need to know the path that this pipe is going to follow. So that's our next sketch. I'll sketch on the front plane. So it's going directly up 400mm, and then going over to the left again another 400. You may choose actually to go more. In fact, let's do that, because I think it will be advantageous to go a bit more. So we'll go 500 by 500. Great thing about parametric modeling, we can change things without having to alter lots of different stuff, and that's great. So now we're going to sweep this profile along this path. So the first thing it's asking me when I hit sweep is what face do I want to sweep. Now I've got to select both of these down here. I could select them individually or wait for them both to highlight, or I could just go to here to sketch one, which is my profile. So I'll click on that, and then it's asking me in red here, click on this, what path do I want it to take? Well, I want it to come up here and round here, and it's drawn it in. Now with only two sketches, it's not too much of an issue about naming, but as you start to go on with Onshape, naming conventions get important, because otherwise you'll be searching through for ages. So it's a good habit to get into. So pipe, profile, now you know what it is, and pipe, path. So that way you know which one's which. And just to make sure it has gone all the way through, I mean we can see they're all the way through, but if we wanted to double check, we could turn the section view on and click just here, and we can actually see through it. And yep, there's a clear path. There's a nasty kink there going around the corner, which is going to cause us some problems with airflow, but hopefully that's what we're about to see. So the great thing about CAD is that we never draw the same thing twice, hopefully, if you're doing stuff right. So here is our pipe. Now because we've made a decent job of it, we can now use this down at the bottom of the tab here. If we right click on this, we can duplicate it. So duplicate, and you'll see here part 3, copy 1. So a copy of that first one. So if we go to that copy, and now we change the path, and maybe we put just a 45 degree, 245 degree bends on here to try and make this, now avoid making it, you see how there it's snapping to the middle. That's okay if you always want it on the middle, but if you accidentally click and lock it to the middle there, you'll struggle to lose that constraint. So if you don't want it in the middle, or you're not sure, click somewhere else. You can always move it and then put it there somewhere. Okay, so we have to decide where the modifications are going to be. So let's put blue lines, obviously mean that it's unconstrained, which means it can be, if we just grab it, you see it can be moved anywhere. We've not given Onshape enough information, so I'm going to say that this dot here to this plane, I'm going to set the information. I'll set that at 300. And I'm also going to set this here, so the angle from there to this plane to 45 degrees. 45 is common for pipe work. And then snip the bits I don't want. Now it's now saying we've got unconstrained areas up here, because this could be, we've now lost a dimension here. So if we put this dimension back in, remember this was ultimately 500, and that line is still blue there, so between there and there should be 5. Yep. So click OK. The sweep's not liking that because we've changed too many things. We've now got 3 lines rather than 2, and it doesn't know what to do. So we'll delete the sweep and put it back in, making sure we use the 3 lines this time. So sweep, asking for the profile face, which is this one. The path, what's this, this, and this. So we've eased the bend round a bit there by having that 45 degrees. We've not made it turn 190 degrees all in one go. So that's one possible solution. Another possible solution, we'll go to, rather than drawing stuff again, I'll click on my original part, right click, create a duplicate, and my duplicate's over is here now, it's copy 2, and I'm going to change this one to something different. This time I'm going to use the radius tool, so radius up here in the path sketch, click on radius. Now it defaults to 5 mm, but once you left click it asks you what you want to do. I'm going to put this as a 200 mm radius. Now again we've gone from 2 lines to 3, so the sweep is not going to like that. So delete the sweep and then re-put the sweep in again. So profile is the face, and the path is this line, and this line. So now we've got 3 different pipe junction models, and now we can go into Simscale and model these and see the differences in airflow. Now we're in Simscale, logged in, we're in the dashboard, we're going to create a new project. I'm only going to do one of these, but the same principles apply to all of them when you're making modifications. So project title, pipe ductwork, and my description, this one is going to be a 90 degree, no radius. Call it something that's meaningful, that you understand what it means. Choose a category, well, ductwork. I suppose that comes under architectural construction. This just helps you finding it later. And also, if you're at university and you're doing lots of different projects, maybe you're doing something for your dissertation, something for a class, make some tag names up for these. That way you can search for your dissertation class or your fluid dynamics class, and they'll all be under the same tag. Just makes things a bit easier to search for. So create a project. Then, because I've created it in Onshape, it should be, and we're looking for, and wait for it to import. It doesn't always give you a lot of warning that it has imported. This import will flash back up again when it's ready, when it's done. Obviously, if you want to import more than one thing, it gives you that option. So that will be done now because that's back highlighted. If we look behind it, yeah, it's there. So that's in place. Now what we need to do is, because this pipe, we've not told the computer where the air is. Is it the air on the outside? Is the actual solid here, is that the air? Is that the fluid? So we need to give the computer some information about what we're actually doing before we even create a simulation. And to do this, you go to the part you just imported in, and add geometry, open inner region. So click on there. You need to click on the two faces that bound where the air is going to be, which is on the inside, but we're going to choose these edges here, that edge, and then just remember that the rotate and mouse operations are the other way in Simscale to Onshape. There are two faces. It needs a face to seed the geometry off. So if you click on that, and just click an internal face. Because otherwise you need to tell it whether it's on the outside or the inside. It needs to know where it is. So just click an internal face. Click start. So take a second or two. It's not a massively complicated geometry, so it won't take ages. And we didn't check keep existing part because we don't want the existing part. So it's going to remove the pipe we've done in Onshape and leave the geometry. Now, in this case, it's not overly complicated, but imagine if this was a manifold or a carburetor or something, or an enclosure of a computer with lots of different components. It would be a lot more complicated, where the air would be. So as you can see, it's got rid of the outside now, and this is the volume that's on the inside of the pipe. This could be air, it could be water, it could be anything. So now we've got that, we can create a simulation. This is going to be reasonably slow air, so we're going to be going for incompressible. If you read the description there, air speeds less than 100 meters per second at standard pressure. Perfect for what we're doing. So menu options, this is going to be going relatively slowly, so laminar flow will be fine. The other option there is steady state or transient. Transient would be like turning the vacuum cleaner on, so going from nothing and how it changes in different steps all the way up to running. We're not overly bothered what this vacuum or what the airflow is going to be like here as it gets up to speed. We're bothered about what it's like when it's fully running, because that's when it's going to be collecting the dust. But there are obviously some states like for example, when the air is flowing out of the exhaust valve of an internal combustion engine, that it's going to be every cycle of the engine that you're going to have exhaust opening, flowing out and stopping. So those transients are important. It does increase the compute time immensely if you change it to transient. So for what we're doing, steady state is fine. So all the geometry is done now. Anything in red needs to be completed. Anything in blue is an advisory, but we're not actually going to do the mesh till we do the simulation run. So material, for this we're looking at air, but we could choose any of these different different materials. So it's already selected the flow region, which is this whole object here. If there's nothing selected here, choose your part. It's got the viscosity and density there already put in, so you've not got to worry about that. Boundary conditions, we've got a few boundary conditions here. So we've got walls, we need to tell it where the walls are, because at the minute it just thinks this is a big blob of air. It needs to know where it's constrained. So here and here, these are walls. Now the reason the walls are important, air's not going to flow through there anyway as part of the model, but what it does is it tells it it's a no slip wall, which means that air molecules will be sticking to the side of it, so the speed will be necessarily slower as we get to the outer wall and faster in the middle. So it gives a more accurate model if we select where the walls are. Next boundary is the inlet velocity. So we see down here at the bottom we've got Z plus. So that's our up and down. So we want it to be going up there. So select that face there because it's in the Z positive. And our Z velocity, I'm just going to put in 10 meters per second. You have to calculate that for yours. So 10 meters per second. And I need to tell it something about the output. I'm going to tell it that the outlet pressure is 0 above atmospheric. There's no difference in pressure there, so leave that as that fixed value. Everything else is blue. I'm going to go to mesh just to make sure the settings are right. Standard, well actually for CFD a hex dominant is a better model, and I think they've found that through experimental, but the hexadedral shape, which is normally a cube, is a better model for fluid flow. It's hex dominant. It doesn't mean that every shape will be a hexahedral, but where possible it will use that. We're modeling an internal mesh, automatic, and we've set it to coarse at the minute, but I'm going to go moderate on this. It's up to you, but obviously the finer the mesh you go, the higher the compute times. Actually, I think I will go for coarse because it is set to automatic. It's going to put more detail around the corners and bits of interest anyway. See what the coarse model's like. If it doesn't give us an amazingly detailed result, we can always go in with a different mesh. So I'm not going to hit generate here, I'm just going to hit the tick, and then I'm going to go to the simulation, run one. I'm just going to put a little note after that, coarse, just so I remember that I've done it on a coarse mesh, and start the simulation. So first of all, this is going to compute the mesh. Once it's done the mesh, it's then going to go automatically on to run the final element analysis for the fluid flow. Once that's done, we'll come back to it. Okay, so that didn't take too long, 4 minutes to do the mesh and the simulation. Now just quickly looking at the mesh, if I click mesh here, we can see it's put this hexadedral mesh on a coarse format on it, and altogether it's used near 26,000 volumes, the majority of which were hexadedra. It's got some prisms and some polyhedra as well to make the shapes up. As we can see, some of them look like four-sided shapes, six-sided shapes. They've got more or less. So then it's done the simulation based on that, and the simulation took just over 4 minutes to do, and we look at the post-process results. Now the good thing about a simulation is you can turn the PC off while that's going on. It's happening on a server somewhere, so you know, if it's the last thing you do before you finish to go to bed or to go to work or something like that, turn the PC off and it'll be done by the time you get back. You can check, it also emails you I think when it's done. So let's have a look at a cutting plane first of all. So it cuts a plane. Now that plane we're not particularly interested in, but that one we are. and I'll click on the face there to get it to. So this is pressure. We're seeing sort of normalish pressure here, and then quite low pressure here, obviously because we're seeing separation because it's such a tight bend. We're also seeing quite high pressure here. High pressure would suggest slow speeds, low pressure would suggest high speeds. So that's our pressure, and we've got big differences in pressure there. That's not a good thing, something you can talk about. Now screenshots, if you just click plus, it puts you a screenshot there, a nice tidy screenshot. You've not got to cut and paste it. You can do as many of these as you want. So next thing on the cutting plane is to look at velocity. Well, we'll look at all velocity for a second. So seeing there, about this colour is in line with this, about 10 meters per second, which was what it was supposed to start at. But here, look, we're seeing an increase in velocity, and then we're up to 25 meters per second at one point. Don't quite know where that is, but we have got some slower regions as well. What we are interested from a dust collection point of view is the Z velocity going up here to start with, and then the minus X velocity going in this direction, which is going to be sucking the dust through. So let's just have a quick look at the Z velocity. This is pretty stable, 10 meters per second, and we see a little bit faster here, but we have got these bits here, look, at minus 2 meters per second, so that's falling. So that's dust that's going up there and is going to be falling back down. It probably won't come out, but it's not an efficient use there. We get some very slow bits there because we've got fast bits here. So that's obviously a problem that you can address hopefully with a radius. And then if we look at the X velocity, that's the velocity in this direction. That's positive, but we're interested in the negative direction. Well, we're seeing here this bit minus 8 meters per second, which is going this way. It's good, it's going to keep the dust moving. But here in the middle we're seeing plus 2 meters per second, which is that way. It's toward the right, which is not such a good thing because it's just blowing the wrong way. So we've got all manner of swirly different things here. Let's take a screenshot of this as well. Hit the plus on the screenshot. It'll put another screenshot there. So we just hit the download button. That was it at the bottom there. So once you've done a screenshot, hit download, and it'll download a nice clean picture of that for you. I'll just, once it's downloaded there, click on it, and that's a nice picture you can stick straight into your Word document with all the scale on the side and everything. Makes it nice and easy. So that's a cutting plane. We can look at different velocities and things like that. Views from our cutting plane, that's quite interesting, but obviously it doesn't give us a picture the whole way through. So I'm going to click the minus on the cutting plane and now look at an ISO volume. This is something that can give us some information as well. So let's look at that Z velocity in a bit more detail, because we were interested in that. Set both of these to Z velocity. Now we've got the max and min values here, so if I turn up the maximum, that's the whole thing. Obviously we can't see all the way through it, we can just see the surface, but I'm interested where these really fast moving parts are. Well, as we thought, those really fast moving bits in the Z direction are here, just as this corner when it whips round. Where's the lowest speed in the Z direction? Well, I would imagine it's going to be up in that top corner. Yep. So we've got lots of Z minus Z here with stuff falling back down. If we change this to all velocity, let's look at it. And we see here we've got a maximum speed from the scale of 25 meters per second. So there are bits of the model where it's going really fast. And because we have continuity of volume going through here, if we have fast bits, that means there must be slow bits somewhere as well. So we can see here a lot of our fast moving is getting close to the edges, this washing round sort of. Look, we can see different things. If we want a screenshot of this, just hit screenshot and it'll give us our different screenshots. Get another one there. So that's ISO volume. The next one we want to look at is a particle trace, to actually see where these air particles are going. Now, when we're in particle trace to start with, it only gives us the silhouette of the part, which can be a bit complicated. So, on particle trace, press plus. We're interested in velocity and all velocity. The radius of these, this is the radius of the traces that are going through. You'll see these in a minute. And this is how many traces by how many traces, because it's going to give us a square. Best to show this by seeing it. So pick, and I'm going to click in the center of this circle here, and as you can see, these are the seeds of where the particles start from. As you can see there, from the center, everything from the center is going up and it's hitting this top, because that's just the way it's going. Now if I want to space these out a bit more, because I want it to cover the bottom completely, just spread it out a bit more, and we can see that it's very chaotic, very nice and steady as it goes up. Then this bend is causing all kinds of problems. Look here at the back, loads of washing round and coming back down and swirling, and also here we've got stuff swirling around here. Now swirling is not a bad thing because it's going to keep the dust moving, but if it loses energy and starts falling back down the pipe, it's not a good thing. Now we've got a fair few particle traces there. We could do a screenshot of this. This would be a good one for our assignment. And we've also got the colour of them here. So when they're going up here, they're all this bluey green colour around this 10 meters per second like we expected. And then all of a sudden we're getting some up here in the 18s, some very dark blue down in the 1s, but we've not quite got enough density there to see. So if we up these to 20 by 20, and then lower the spacing down so they're more densely together, we can now see there's some quite slow moving areas here. Some really fast moving, some really slow moving. We could also have the seed, rather than being on the intake, we could have it on the exit. There, just click there. And we see there what's happening, lots of different sort of washing around. Once we've done our particle trace, if we want to look at this being animated and see where those particles go, if we go to animation, we have to have done the particle trace already. Change it to particle trace, hit apply, just wait for it, and we'll see the air particles going up there and where they're swirling around. Now this is quite a blocked view, and part of that, if we go back to particle trace, is because of the radius of these particle traces. We can drop that down to its thinnest. That way they become really thin and a bit easy to see a lot of them. And you can zoom in on different bits as well. We can see here that some of the air particles are really taking a long path and swirling around all over the place. And also here we've got a lot of turbulent airflow around here as well. So hopefully if you've managed to get this far, then the other models you did in Onshape, so this is the one we've just modelled, then there's this one with a radius and this one with a 45-degree bend. So you're going to need to model all of these, and maybe even with the radius, see what a 200mm radius does, see what a 100mm radius does, see what a 300mm radius does. The correlation is between steady state of air and radius size.